Into the darkness of space and the vastness of the cosmos, two small human-made objects speed across the boundaries of the solar system, continuing their journey into interstellar space after leaving the heliosphere. Their mission was not only to explore the giant gas planets and study outer space, but also to carry a message from humanity to the possibility of other life beyond Earth. Let us get to know this remarkable human achievement, a project known as Voyager. Between 1962 and 1973, NASA and the Jet Propulsion Laboratory launched a program called Mariner, aimed at sending a series of robotic interplanetary spacecraft to study Mars, Venus, and Mercury. This program became the foundation and precursor to the creation of two unmanned spacecraft later known as Voyager 1 and Voyager 2. Originally, the Voyager spacecraft were part of the Mariner program and were initially named Mariner 11 and Mariner 12. However, NASA later moved them into a separate program called Mariner Jupiter-Saturn. Their names were changed when the spacecraft designs were considered to have evolved significantly beyond the original Mariner missions. At that point, their objectives also changed, and Voyager was given its own distinct mission. The Voyager program closely resembled the planetary Grand Tour, a concept developed in the late 1960s and early 1970s. This plan took advantage of a rare alignment of the outer planets, discovered by aerospace engineer Gary Flandreau at the Jet Propulsion Laboratory, which allowed spacecraft to use gravity assists to travel between planets. This planetary alignment occurs roughly once every 175 years and was expected to happen again in the late 1970s, making it possible to explore Jupiter, Saturn, Uranus, Neptune, and Pluto using gravitational assistance. Unfortunately, due to limited funding, the planetary Grand Tour program was eventually cancelled. However, its mission goals and spacecraft elements were incorporated into the Voyager program, which ultimately fulfilled nearly all of the Grand Tour's planetary objectives, except for the mission to Pluto, which was still considered a planet at the time. The two Voyager spacecraft were designed as unmanned space probes. Although similar in design, they differ in weight. Voyager 1 weighs approximately 1,616 pounds, while Voyager 2 weighs about 1,797 pounds. Despite this difference, both travel at nearly the same speed, around 61,198 km per hour or 38,027 miles per hour, far exceeding the speed of modern fighter jets, which typically reach between 1,200 and 1,900 miles per hour. The Voyager spacecraft were designed by the Jet Propulsion Laboratory and equipped with 16 hydrazine thrusters, 3-axis stabilization, gyroscopes, and celestial reference instruments, including sun sensors and a Canopy star tracker. These systems allow the spacecraft to keep their large parabolic antennas precisely pointed toward Earth, enabling data transmission through the deep space network. Voyager communicates with Earth using S-band and X-band frequencies, achieving data transmission rates of up to 115.2 kilobytes per second near Jupiter. This rate gradually decreases as the spacecraft moves farther away from Earth. Even when direct communication becomes limited, Voyager carries a digital tape recorder, DTR, capable of storing approximately 64 megabytes of data for later transmission. Both spacecraft are equipped with 11 nearly identical scientific instruments designed to study celestial objects throughout their journey. However, Voyager 2 was given additional upgraded instruments, such as cameras, spectrometers, and an enhanced magnetometer, specifically intended for exploring Uranus and Neptune. Inside each spacecraft are 3 multi-100-watt radioisotope thermoelectric generators, RTGs. Each generator contains 24 plutonium oxide spheres, producing heat that is converted into electricity. At launch, each RTG generated about 157 watts, for a combined total of approximately 470 watts. This power output decreases by half every 87.7 years due to radioactive decay. These generators allowed Voyager to operate well into the 2020s, providing enough power to support 5 scientific instruments until early 2023. In April 2023, engineers at the Jet Propulsion Laboratory began using reserve power originally intended for onboard safety systems. This adjustment extended the mission further, allowing the remaining 5 scientific instruments to continue operating, with projections suggesting they may remain active until around 2026. Voyager's 16 hydrazine thrusters provide attitude control, are used for trajectory correction maneuvers, while the rest stabilize the spacecraft. The onboard titanium fuel tank, containing approximately 100 kilograms of hydrazine, is estimated to be sufficient to extend the mission until around 2034.
4, 3, 2, 1. We have ignition, and we have liftoff.
Voyager 2, although completed earlier, became the first Voyager spacecraft launched by NASA on August 20, 1977, from Space Launch Complex 41 at Cape Canaveral, Florida. Voyager 2 was sent on a long, looping trajectory designed to study the outer planets and interstellar space beyond the Sun's heliosphere. Its planned path would take it past Jupiter, Saturn, Uranus, and Neptune. 16 days later, on September 5, 1977, NASA launched Voyager 1 on a different trajectory, allowing it to reach Jupiter and Saturn faster than its twin. Its mission focused on flying past Jupiter, Saturn, and Saturn's largest moon, Titan. Voyager 1 studied the weather, magnetic fields, and ring systems of both planets, becoming the first spacecraft to provide detailed views of the natural satellites of Jupiter and Saturn. On December 10, 1977, both Voyager spacecraft entered the asteroid belt at the same time. Just 9 days later, on December 19, 1977, Voyager 1 overtook Voyager 2 due to its faster trajectory. In April 1978, Voyager 2 experienced a serious complication when communication was interrupted after no commands were sent for a period of time. Its primary radio receiver failed to transmit data. As a result, the remainder of the mission relied on backup communication systems, and the main radio receiver was later confirmed to have permanently lost the ability to send or receive signals from Earth. Engineers were still able to continue the mission by calculating and transmitting signals at specific frequencies that Voyager 2 could receive. On October 21, 1978, Voyager 2 exited the asteroid belt and began its journey toward its first planetary target, Jupiter. Along a different and faster path, Voyager 1 entered Jupiter's region and began its observations on January 6, 1979. Voyager 2 followed several months later, starting its observations on April 25, 1979. Voyager 2 conducted more detailed observations of Jupiter, approaching as close as 570,000 kilometers. It revealed that Jupiter's Great Red Spot is a complex storm rotating counterclockwise across the planet's surface, surrounded by smaller storms and vortices within Jupiter's banded cloud layers. Voyager 2 transmitted high-resolution images of Jupiter and its moons, including Amalthea, Ganymede, and Europa, back to Earth. It also confirmed Voyager 1's discovery of active volcanism on Io. With no major obstacles at this stage, both Voyager 1 and Voyager 2 continued onward to their next missions after successfully sending high-resolution images and video data of Jupiter to Earth. NASA continues to monitor their trajectories and receive data from them on a regular basis. Voyager 1 reached Saturn's orbit on August 22, 1980, and began detailed observations of the planet, followed by an extended study of Saturn's largest moon, Titan. Its observations at Saturn lasted longer than those at Jupiter, before Voyager 1 left the Saturnian system and officially extended its mission on December 14, 1980. Voyager 1 is recorded in history as the spacecraft that provided the first high-resolution images of the moons of Jupiter and Saturn, including Callisto, Io, Titan, Ganymede, and several other natural satellites of both planets. It also made the groundbreaking discovery of active volcanic activity on Io, something that had never been observed before by telescopes or by previous missions to Jupiter, such as Pioneer 10 and Pioneer 11. This is largely due to Io's extremely close orbit around Jupiter, which causes intense geological activity driven by Jupiter's powerful magnetic field. During its visit to Saturn, Voyager 1 reached its closest approach on November 12, 1980, passing within approximately 124,000 kilometers of Saturn's cloud tops. Its mission to study Saturn's rings and moons, especially Titan, was highly successful. Titan became the final object within the solar system observed by Voyager 1 before the spacecraft was directed toward interstellar space. According to data released by NASA on August 25, 2012, Voyager 1 successfully crossed the heliosphere and entered interstellar space, making it the first spacecraft in history to leave the solar system. On December 12, 2023, NASA announced that Voyager 1's flight data system could no longer use its telemetry modulation unit, preventing the spacecraft from transmitting scientific data back to Earth. As of now, NASA has not been able to confirm whether Voyager 1 can continue its mission, which has lasted for more than 49 years. Meanwhile, due to its longer and more curved trajectory, Voyager 2 entered Saturn's orbit later, on June 5, 1981, and began its observation phase. Voyager 2 made its closest approach to Saturn on August 26, 1981. After passing Saturn, Voyager 2 experienced damage to its scanning platform, resulting in the loss of some data. This posed a serious challenge to the continuation of its mission. However, engineers on Earth were able to recover parts of the system, allowing Voyager 2 to continue its scanning operations, although not at full performance as before. The object, which appeared extremely small in outer space, continued its mission toward Uranus, entering orbit and beginning its observation phase on November 4, 1985. Voyager 2 made its closest approach to Uranus on January 24, 1986, at a distance of 81,500 kilometers above the planet's cloud tops. Voyager 2 also discovered 11 previously unknown moons: Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Belinda, Puck, and Perdita. In addition, Voyager 2 successfully measured that 1 day on Uranus is equivalent to 17 hours and 14 minutes on Earth. Several other new features were also discovered, including rings, geological fractures, and atmospheric magnetic waves unique to Uranus and different from those of other planets. With these increasingly detailed observations, Voyager 2 required a very long time to explore the solar system, as its mission was primarily focused on planets orbiting within it. Even on August 20, 1987, 10 years after its launch, the spacecraft was still within the solar system, while its twin had already traveled far beyond the heliosphere and into interstellar space. Voyager 2 continued its mission to explore Neptune after successfully entering its orbit on June 5, 1989, and officially began its interstellar mission on October 2, 1989. Every movement of Voyager 2 was carefully tracked and monitored. NASA sent Voyager on this interstellar mission to better understand what lies beyond the heliosphere. In 1992, Voyager 2 transmitted data to Earth containing observations of nova V 1974 Cygni in the far ultraviolet spectrum. Later, in July 1994, Voyager 2 sent additional data from observations of the impact of fragments from comet Shoemaker-Levy 9 with Jupiter. At that time, Voyager 2 was estimated to be within range of the event. However, it failed to detect anything, as calculations showed that the fireball occurred just below the spacecraft's detection threshold. As time passed, Voyager 2 continued to move farther away from Earth. By August 20, 1997, the human-made spacecraft had been operating continuously for 20 years, 2 long and highly significant decades for humanity. Unfortunately, as Voyager 2 aged and traveled farther, its capabilities gradually declined due to diminishing power. On November 13, 1998, NASA implemented power-saving measures to allow Voyager 2 to continue operating for a longer period. Engineers ultimately decided to shut down the ultraviolet scanning and observation platform. A problem was detected on November 29, 2006, when a telemetry command sent to Voyager 2 was misinterpreted by the onboard computer as an instruction to activate the spacecraft's magnetometer electric heater. As a result, the heater remained on until December 4, 2006. During those days, Voyager 2 reached temperatures exceeding 130 degrees Celsius, far above the magnetometer's tolerance limits. Half a year after that incident, Voyager entered the third decade of its space journey, precisely on August 20, 2007. This marked the fact that Voyager 2 had spent 30 years exploring regions of space never before reached by humans. 10 days later, on August 30, 2007, Voyager 2 was recorded crossing the termination shock and entering the Helio sheath, approximately 1 billion miles closer to the Sun than Voyager 1. Next, on September 6, 2007, NASA decided to shut down the data tape recorder operating system, which was considered no longer necessary. The system had previously failed and had not functioned properly since June 30, 2002. This was followed on February 22, 2008, when NASA deliberately shut down the planetary radio astronomy experiment on Voyager 2 to conserve power. About 2 years later, on April 22, 2010, Voyager 2 experienced a scientific data formatting problem. According to engineers at JPL, this incident was caused by a bit system error in the onboard computer. A system reset was carried out on May 19, 2010, to correct the error, and on May 23, 2010, Voyager 2 successfully resumed transmitting scientific data from deep space. On November 7, 2011, Voyager 2 switched to its backup thrusters to conserve power and extend its mission. As its available power continued to decline, Voyager 2's speed gradually decreased. Nevertheless, the spacecraft continued its steady journey. By the end of 2012, its trajectory was directed toward the constellation Telescopium. Voyager 1, traveling about 2 billion miles ahead, continued to transmit data to Earth. In 2013, Voyager 1 was moving away from the Solar System at a speed of 540 million kilometers per year, while Voyager 2 was traveling at approximately 490 million kilometers per year. Initially, Voyager 2 was expected to enter interstellar space in early 2016. However, even by August 20, 2017, marking 40 years of Voyager 2's flight through space, it had not yet crossed the heliopause. It was not until November 5, 2018, that Voyager project scientist Edward Stone announced that Voyager 2 had finally crossed the heliopause and entered interstellar space. Meanwhile on Earth, NASA was required to perform maintenance on the Deep Space Network, which forced the agency to suspend contact with Voyager for 8 months in 2020. Communication was re-established on November 2, 2020, when a series of commands were successfully transmitted and acknowledged by Voyager. Full communication with Voyager was fully restored on February 12, 2021, after major upgrades to the ground station antennas were completed, a project that took approximately 1 year to finish. On July 18, 2023, Voyager 2 surpassed Pioneer 10 to become the second most distant spacecraft from the Sun. Several challenges occurred shortly afterward, including a software error on July 21, 2023, which caused Voyager 2's Earth-pointing antenna to become misaligned, resulting in a temporary loss of communication. A system reset on August 4 enabled Voyager 2 to autonomously reorient its antenna back toward Earth. In 2023, NASA also implemented a software update to redirect power away from the voltage regulator in order to keep the scientific instruments operating. At present, Voyager is expected to run out of power to continue operating its scientific instruments around 2030 and will be beyond the reach of the Deep Space Network by 2036. Even so, Voyager will continue moving forward, traveling through the dark and vast expanse of space solely on its mission to cross interstellar space. Throughout its mission, Voyager has transmitted a vast amount of data and high-resolution images back to Earth. However, perhaps the most memorable contribution for humanity is the final photograph sent on February 14, 1990, from a distance of about 6 billion kilometers from Earth. Voyager 1 captured a panorama of the solar system now known as the Family Portrait. This panorama consists of images representing 6 planets in the solar system, along with a background showing their relative positions. The image is a mosaic composed of 60 individual photographs. It became the final set of images taken by Voyager, as both Voyager 1 and Voyager 2 transmitted only telemetry data afterward. One of the images in this collection is the photograph of Earth known as the pale blue dot, popularized by Carl Sagan, who was a member of the Voyager publication team at the time. In the image, Earth appears as less than half a pixel, just a tiny dot in the vastness of space, suspended within bands of sunlight scattered by the camera's optics against the surrounding blackness. After completing its primary mission in the solar system and preparing to leave it for interstellar space, Voyager 1 was instructed by NASA to turn its camera back toward Earth and capture this image of our planet within the immense universe. This photograph was taken at the request of Carl Sagan, the astronomer who played a key role in the Voyager mission. For nearly 49 years, Voyager has journeyed through the boundless reaches of space while carrying a message from Earth. Yes, this is something that is often overlooked. Both Voyager 1 and Voyager 2 carry the Voyager Golden Record, a gold-plated audio-visual disc containing a curated collection of messages from Earth, intended to demonstrate the richness and diversity of human culture, science, and life on our planet. NASA created the Voyager Golden Record with the intention that other beings in space might one day communicate with humanity. The contents of the Golden Record were developed under the guidance of a team of distinguished figures in their fields, including Carl Sagan and Timothy Ferris. As an introduction to the Golden Record, the team included an opening message featuring greetings from the US President at the time, Jimmy Carter, as well as the Secretary General of the United Nations, Kurt Waldheim. Recordings of natural sounds, also known as the sounds of Earth, include ocean waves, wind, birds, other animals, a baby's cry, human speech, music, and instructional sounds. Music from various cultures around the world was also included, spanning Western classical compositions, traditional music, and ethnic music from different countries. Among the selected works are pieces by Wolfgang Amadeus Mozart, Blind Willie Johnson, Chuck Berry, and Valia Balkanska. In addition, greetings and messages in 59 different languages were recorded to address any extraterrestrial beings who might listen to the disc. The record also contains images depicting many aspects of life on Earth, including humans, animals, natural landscapes, structures, architecture, and scientific illustrations such as the structure of DNA and the human body. Beyond this, NASA included instructions for playing the audio and visual recordings, engraved in binary code and accompanied by diagrams to explain how the information should be interpreted. There is also a location map in diagram form showing Earth's position within the solar system, as well as the positions of nearby stars and galaxies that might be recognizable to extraterrestrial civilizations. NASA further provided technical and scientific data about Voyager itself, including its design, technical specifications, and information about the time and location of its launch. Despite the remarkable achievements of the Voyager missions and the impressive concept of the Voyager Golden Record they carry, the inclusion of the record has in fact generated long-standing debate and controversy regarding its contents. One of the main points of criticism is that the Voyager Golden Record is considered not to fully represent the diversity and complexity of life on Earth. In addition, several images depicting nude human figures have been regarded by some as inappropriate to be sent as a message representing humanity to potential extraterrestrial life. Furthermore, some individuals, including Stephen Hawking, have argued that sending messages into space through the Voyager Golden Record is ethically irresponsible. The concern is that it could attract the attention of technologically advanced intelligent beings who may not have friendly intentions toward humanity, thereby posing a potential threat to life on Earth. Hawking suggested that if extraterrestrial civilizations were capable of discovering humanity, they would likely be far more advanced and might view us as insignificant, comparable to bacteria. The extraordinary exploration carried out by Voyager 1 and Voyager 2 continues to this day, pushing beyond the farthest boundaries ever reached and remaining observable through NASA's monitoring systems. The presence of these two spacecraft stands as a human achievement that reflects the depth of our curiosity and our desire to understand a universe that is vast, mysterious, and possibly limitless. The seemingly endless journeys undertaken by Voyager 1 and Voyager 2 have expanded, and will continue to expand, the boundaries of human knowledge, offering us a perspective on the beauty, complexity, and wonder of outer space. Voyager is not merely about physical exploration, but also about spiritual and philosophical exploration, helping humanity seek answers to questions that remain unresolved.